today we are very pleased to welcome Caitriona Jackman. She's an honorary professor at the Dublin Institute for Advanced Studies. She's currently also a fellow at the Alan Turing Institute. So Caitriona's expertise centres on planetary magnetospheres, understanding auroral processes, and exploring how machine learning and complexity science can be used to study huge volumes of data from space. So today, Caitriona will be speaking on the solar wind influence at the gas giant planets. We'll have Caitriona's seminar. If you have any questions throughout, you can just pop them into the chat and we'll go through them at the end. So I'll hand it over to you now, Caitriona.
Thank you very much, Jasmine. Good morning, everybody. Nice to know that you're all here. So today I'm going to talk to you about how the sun can influence the dynamics of the magnetospheres of Jupiter and Saturn. Starting off by showing this common picture of the Earth and the sun emitting a large coronal mass ejection, and that flow of solar wind shaping the Earth's magnetosphere, flowing mostly around the boundaries, but having some interaction which in turn drives some very complex magnetospheric dynamics. So to place the outer planets or the gas giants into context, let's start with this schematic figure. And it shows the magnetospheres of Mercury, Earth, Jupiter, and Saturn. And so magnetospheres generally have a fairly similar shape, but in the case of these four, their sizes and their properties are very, very different. So when we think of Mercury, it's a small planet, very close to the sun. The solar wind has a really, really strong influence there. In fact, sometimes perhaps so strong that you actually completely lose the resistance to the sun, and you actually could have potentially direct entry of the solar wind onto the surface of the planet. So it's a small standoff and a small magnetosphere, and one that is entirely driven by solar processes. Then Mercury's magnetosphere fits into a tiny portion of the Earth's. So Earth, I know there are many terrestrial magnetospheric scientists in the MIST community, very well sampled magnetosphere, and again, one that is driven by the interaction with the solar wind. And then when we go out to 5 and almost to 10 AU with Jupiter and Saturn, we have a different picture. So we still have the solar wind attempting to exert an influence on these magnetospheres, but they provide some competition in the form of rapid planetary rotation, strong planetary magnetic fields, and internal plasma sources. So Jupiter, for example, has the volcanic moon Io, and you can see the Io plasma torus shown in orange here. And Saturn has the moon Enceladus, which also acts as a significant source of plasma internal to the magnetosphere. And so, you know, I'll say it once now and probably several times throughout this talk, there is a big debate at the outer planets as to the extent to which external versus internal dynamics can control the picture. So how does the solar wind compete with planetary rotation and with internal plasma to drive dynamics in those systems? So today I'm going to talk primarily about the sun and the solar wind and what that is doing and how it can exert some influence in those environments. So what I'm going to do is take you on a journey in terms of understanding the solar influence, starting by looking at interplanetary space and what we can measure upstream of these planets, then getting closer to the planets, looking at the magnetospheric boundaries, and then finishing off by looking a little bit at remote sensing and how we can use things like auroral physics to give us a hint as to what the sun and the solar wind are doing. But first off, how do we know what we know about Jupiter and Saturn? So what kind of data sets do we have available to us? Well, at Jupiter, here's a really nice diagram which shows some of the spacecraft which I've visited. Not all, it's missing New Horizons and Cassini, but it shows some of the flybys, so Pioneer, Voyager, and Ulysses. Ulysses has the slightly different trajectory shown in brown. And then the 2 orbital missions, so the Galileo mission, and then of course Juno. And you couldn't mistake Juno's orbit for anything else because it's just very, very clear, starting at in the dawn sector and then sort of precessing around towards the magnetotail. At Saturn, we've had 3 flybys, Pioneer 11, Voyager 1 and Voyager 2, and then Cassini, which orbited from 2004 and finished up in 2017. So on the right-hand side here, I'm showing you Jupiter on the top and Saturn on the bottom, the international sunspots number as a function of time from 1970 to 2020, and showing you the times of those flybys and orbital missions. So at Jupiter, we've got coverage at different stages of the solar cycle with flybys, and then with the Galileo orbiter, and then Juno is actually hidden under here. Juno from 2016 and hopefully continuing through 2021. At Saturn, all the flybys happened at or close to solar maximum. And then one of the things that was so special about Cassini is that Cassini was a very long duration mission. So it arrived at Saturn during the declining phase of the solar cycle back in 2004, and it encompassed a solar minimum and all the way through to the next solar maximum. And so that gives us an amazing opportunity to study Saturn across planetary season, but also across solar cycle, and to really give you an insight into how changes in the upstream dynamics can have an influence on what's going on in the magnetosphere. I still find it quite difficult to talk about Cassini in the past tense, having spent so much time working on it during my career. Okay. Oh, the subtitles now seem to be about 5 minutes behind. That's fine. Okay. So let's start by looking at the interplanetary medium. So what are we seeing upstream of Jupiter and Saturn? Well, it's common out at 5 and 9 AU for the structure of the interplanetary medium to be dominated by something called co-rotating interaction regions, which I often think of a bit like an interplanetary traffic jam, where you have these bands of fast and slow solar wind, which are being emitted from the sun. Those field lines are fixed to the surface of the rotating sun. And so with increasing distance in the heliosphere, those bands of fast and slow wind start to interact. And on the top left here is a cartoon showing how that interaction works, where you have the slow wind, the central gray panel, and then the fast wind around it, and what's called the heliospheric current sheet embedded in the middle of the slow solar wind. And then you have forward and reverse shocks propagating at the points where those different solar wind populations are interacting. But what does that actually look like in a data set? Well, here on the right, I'm showing you some data from the Cassini magnetometer instrument. And this was during Cassini's time when it was upstream of Saturn, so sampling the interplanetary medium at beyond 9 AU. And we're looking in RTN coordinates, RTN, and then the total magnetic field strength. But if we just start by looking at this bottom panel, what we can see is that the interplanetary medium at Saturn is highly structured by compressions and rarefactions associated with these co-rotating interaction regions. So we see regions of rarefaction where our interplanetary magnetic field strength is of order, less than 0.5 nanotesla. And then we see compression regions where our interplanetary magnetic field strength can get up to 1.5 nanotesla or more. And those compressions have embedded within them these crossings of the heliospheric current sheet, which we identify by changes in the sign of this BT component. So we do see a very strong structuring, particularly during the declining phase of the solar cycle, when the sun's dipole is tilted. We see a strong structuring of the IMF by these co-rotating interaction regions. And actually that turned out to be very useful at Saturn, because when Cassini was approaching, we had several solar rotations. I should say this plot is over one solar rotation, so 25.5 days in this case. We had several solar rotations before Cassini arrived at Saturn, where we were sampling the interplanetary medium, and we could see this regular phasing of rarefactions and compressions. And so that actually enabled us to predict when Cassini entered Saturn's magnetosphere when the next compression was coming. So that's quite a useful property of the solar wind, is its regularity. I think a really nice and really important thing to consider is that the solar wind that we measure at the Earth at 1 AU is not the same solar winds as we're seeing at Jupiter and Saturn. And that's illustrated really nicely by this figure, which was from Hanlon et al. In 2004. And it's the output of an MHD simulation, which shows how the magnetic field evolves. So time increasing down along the y-axis, and then heliospheric distance here out to 5.5 AU. And so we see small blips in the magnetic field start to steepen into shocks and into what we might sense as these kind of compression regions. But actually, by the time this solar wind had made its way out to about 4 AU, these compressions had merged into what's called a merged interaction region. And so that evolution and that behavior of the magnetic field needs to be considered, and it's very important to remember that what we see at 1 AU is really of a very different character. Okay, in addition to measurements of the magnetic field, and we can also measure the plasma properties of the solar wind if we have plasma instruments on our spacecraft. And so what I'm showing you here are some distributions of some common plasma parameters in the solar wind at Jupiter for the top panels and at Saturn for the bottom panels. And so those plasma parameters are the alphane Mach number, fast mode Mach number, the solar wind dynamic pressure, nanopascals, and the plasma beta. For Jupiter, I'm able to distinguish between solar max in red and solar min in blue. If you think back to that figure a couple of slides ago, where I showed the solar cycle and all of the different missions that visited Jupiter, we have coverage at all stages. And so we're able to compare and contrast. And there are some small differences. At Saturn, the data that I'm showing are only from solar maximum. So they're only from the Pioneer and Voyager era. And that's because Cassini was a 3-axis stabilized spacecraft. And so it had a plasma instrument, which was tacked onto one side of the spacecraft, and it was on an actuating platform. But because the spacecraft wasn't spinning, it wasn't always able to get a full picture of the sky, and so it wasn't always able to get reliable plasma moments, particularly in the solar wind. So these Saturn distributions are from solar max, from the Pioneer and Voyager era. But broadly speaking, from the plasma parameters, the Mach number distributions show a highly supersonic and a superalphanic flow. And then we can also have things like these distributions of solar wind dynamic pressure to give us a baseline for what we think is the typical and the extreme behavior that we're seeing at these planets, and to place our observations in the context of those distributions. When we're lacking an upstream monitor, which we generally are at the outer planets, if we're inside the magnetosphere and we're wanting to know what's going on upstream, it can be really useful to take advantage of models. And so there are several models that are used. Some that are most commonly used, there's one called MSWIN, which comes out of Michigan, and then there's a model which is led by Chihiro Tao. And all of the data associated with those are freely available if you follow these references. So what those models do is they are one-dimensional MHD models which take omni data from the Earth and propagate it out in the heliosphere. And they produce things like modeled solar wind speed, solar wind density, or IMF strength. And you can compare and validate these models with propagated data compared to observations. There is an error on things like the shock arrival time, and that is a function of things like how far you are from opposition. But those models can be really useful to give us a context for what's going on upstream, particularly when you don't have an upstream monitor. So I talked at the beginning about this kind of competition between external and internal drivers, but actually the sun can almost be a bit sneaky in that it can also affect the internal drivers. And what I mean by that is that the solar influence can actually change the plasma production rates inside a magnetosphere. So at Jupiter and Saturn, the volcanic moons Io and Enceladus produce neutral material, and that forms in this kind of a torus or a donut around the planet. That neutral material can then become ionized by different processes, so electron impact ionization or photoionization. But work has shown that those reaction rates can change by a factor of up to 5 with solar cycle, and lots of things change with solar cycle. Here I'm showing you, a couple of examples of different properties which change. From the radio flux to the core to wing ratio and things like EUV irradiance. But the reaction changes that are involved in the production of these plasma tori are maximizing at solar maximum. And so what we would expect is that at solar maximum, we have more plasma produced internally in a magnetosphere, which in turn is going to have knock-on implications for how much material you need to get rid of. Because if you produce plasma inside a magnetosphere, ultimately it's going to need to be transported and then lost, because the magnetosphere isn't just going to inflate forever. So in that sense, the sun can have a direct impact on plasma production, but the sun can also have a direct impact on things like conductivity. So here, when I'm showing EUV irradiance, that has been shown to be linked directly to conductivity. So that's modulated by the solar cycle, and conductivity matters hugely because increased conductivity can lead to an increase in things like field line currents and accelerating voltages and precipitating electron energies. And so higher conductivity can mean brighter aurora. So the sun can have a direct influence in that sense. Okay, moving on to out from interplanetary space towards the magnetospheric boundaries, a region which can tell us a lot about what the upstream drivers are is the magnetosheath. So the region between the bow shock and the magnetopoles, which contains this shocked, compressed, heated solar wind plasma. And we have lots of measurements of the magnetosheath. So Juno didn't plan to take lots of measurements of the magnetosheath. Initially, the plan for Juno was that it would be on a series of 14-day orbits around Jupiter, which would constrain it more tightly to Jupiter's sort of inner magnetosphere. But there was a change of plan, and when Juno arrived, for various reasons, it ended up that the Juno orbits were kept at 53 days. So what that meant is that Juno apogee, and here I'm showing you the Juno trajectory here, Juno apogee, so its furthest point from the planet, is actually at about 100 to 115 Jovian radii. And so for the Juno orbits which were on the dawn flank, that meant that the spacecraft was sampling quite a bit of time in the magnetosheath. So here are some sort of magnetopoles curves and the Juno trajectory overlaid. And so we have an extensive set of magnetosheath measurements at Jupiter, and there have been many studies done on the magnetosheath. I've just selected one. And in this particular study by Ranquist et al., they found things like, they studied the statistical properties of the magnetosheath plasma. They found, as we might expect, a slowest velocity near the magnetopole's nose and a decrease in plasma temperatures down tail. But they also found quite thick boundary layers near the magnetopoles. And they suggested that this may link to the presence of significant Kelvin-Helmholtz vortices. And we know that Kelvin-Helmholtz is a way for there to be direct entry of solar wind plasma into the magnetosphere, as opposed to, say, Dayside reconnection, which I'll talk about in a minute. And so the magnetosheath really gives us that opportunity to have a window on the solar wind interaction. At Saturn, we also have lots of magnetosheath measurements. Here is a figure showing the location of boundaries and the plasma flow vectors, giving you an indication of how the plasma flow is deflected at Saturn. And Michelle Thompson wrote a great paper. I'm slightly biased because I am a co-author on it, but Michelle Thompson is amazing. So she wrote this paper in 2018 where she took all of the magnetosheath measurements from Saturn and developed a new method to infer the upstream solar wind speed from the magnetosheath proton temperature. And that method is based on there being a rough equivalence between the upstream and downstream energy per particle. So the bulk flow that enters into the bow shock is then transferred into a slowed flow energy, a thermal energy, and a magnetic field energy. And that summed energy can be measured by the Cassini plasma spectrometer instrument, and it can then be, it's found to be able to convert it into a solar wind speed. So that's a really great opportunity to take these magnetosheath measurements and use them as a kind of an upstream monitor. Okay, I mentioned reconnection, and I'll say at the outset with this slide that the role that Dayside reconnection plays at the outer planets is hotly debated, and there are many different views on this, and I've tried to be as representative as I can of those views, bearing in mind, of course, my own experience and biases. So in that vein, I'll start by referencing some work that I've done on this topic. And many terrestrial scientists will recognize an equation of this form, which describes something called the Dayside reconnection voltage. So essentially, we're trying to quantify the rate at which Dayside reconnection at the magnetopoles can open flux and contribute to that cycle of opening and closing of flux in the magnetosphere, and reconnection between the interplanetary magnetic field and the planetary field. So the rate at which that reconnection happens is found, in the case of the Earth, to be a function of parameters like the solar wind velocity, like the planetary magnetic field, like theta, which is a clock angle, and this value L0. And L0 can almost be thought of as a length or a segment of the magnetopoles that is unstable or susceptible to Dayside reconnection happening. And empirically from Earth, that's found to typically be about half the magnetopole standoff distance. So I adapted this for the case of Saturn. So the magnetopole standoff distance at Saturn is typically about 22 to 27 Saturn radii, but I just took a round value of, say, 10 RS, and then a sort of sensible solar wind velocity. And this has also been done for Jupiter by Nichols et al. And from these Dayside reconnection voltage values, you can then get a cumulative amount of open flux that is added to the system and compare it with things like auroral imagery and see how that Dayside reconnection is impacting the dynamics of the magnetosphere. But as I say, there is a lot of debate about the efficiency of reconnection and all of the things that can impact on that efficiency. So for example, there are several studies done about the effect of changing Mach number on reconnection efficiency, with some suggesting that the efficiency decreases with increasing Mach number and others suggesting that it doesn't play a role. There are studies showing that the efficiency can decrease with a large plasma beta in the sheath, others saying it's only the change in plasma beta across the boundary that matters. There are studies looking at the effect of flow shear, and some which show that there is a more severe diamagnetic drift suppression at Saturn, for example, than there is at the Earth, and that may limit the onset of reconnection to higher magnetic shear conditions. But I will just say there are many studies which have shown evidence of Dayside reconnection happening at these planets. So there are examples at Saturn, including the publication of a flux transfer event at Saturn's Dayside magnetopoles. And at Jupiter, most recently with the Juno spacecraft, there is evidence of reconnection happening at the magnetopoles there. So it happens. The degree to which it controls things inside the magnetosphere is one that's, I would say, still a very open debate. Okay, I'm showing my Saturn biases a little bit now, because I'm just gonna focus briefly on Saturn only when we consider what the magnetospheric boundaries can tell us about the influence of the solar wind. And here are some figures from a study from 2019, where I compiled a complete list of all magnetopause and bow shock crossings from the entire Cassini mission, building on the work, excellent work of others, including Nathan Pilkington, who focused primarily on the magnetopause. So here on the left, showing all of the magnetopause crossings from Cassini and overlaying the model curves from Sheila Kanani's model for compressed and expanded conditions. On the right, I'm showing in blue every bow shock crossing that Cassini made, and overlaid the bow shock model of Daniel Wendt, again for compressed and expanded conditions. So what can you do with a gigantic text file of lots of timings of crossings? Well, if you want to study solar wind influence, you can use it to select out portions of the Cassini dataset where you're in the solar wind or where you're in the magnetosheath, and do statistical studies on those. You can also do things like using the times and positions of the crossings themselves to infer upstream parameters. So you can take a crossing anywhere, and you can use magnetopause and bow shock models to track that crossing back to the nose, look at the nose standoff, and look at the associated inferred solar wind dynamic pressure, and then compare that, for example, to models. Here's this Michigan MSWIM model that I mentioned earlier. So we've done that and compared the inferred dynamic pressure from magnetopause crossings, shown here in black, bow shock crossings in red, and a model. And we do find some differences, most stark, I would say, when we compare with the bow shock crossings. But if we think about what we're actually measuring with Cassini, of course, we can only record a bow shock crossing when Cassini is in the position where the bow shock is. And due to the nature of the orbit of Cassini, most of its time was spent relatively close to the planet. And so statistically, you will find that the times when it encounters a bow shock are more likely to be the times when the bow shock is that little bit more compressed in. So that would tie with this picture of, on average, a slightly higher solar wind dynamic pressure. But the solar wind can do really dramatic things to these boundaries. And here I'm showing some examples of pairs of crossings. So we had lots of times when we had a crossing of the bow shock inbound, followed by a crossing of the magnetopause inbound, or vice versa, magnetopause outbound, followed by bow shock outbound. So a pretty quick traversal of the magnetosheath. And there were about 40 pairs out of this list that had magnetosheath traversals that were 300 minutes or quicker. And what I did was looked at those and looked at things like how you can infer the velocity of the nose of the magnetopause. And typically that velocity is about 10 kilometers per second. But during some of these cases where you have a really rapid traversal of the magnetosheath, that implies that between crossing one boundary and crossing the other, you had a really strong compression by the solar winds. And our calculations indicate that during a very, very strong compression, you can have a magnetopause nose velocity of up to 263 kilometers per second. So the solar wind is really able to exert a very dramatic effect on Saturn's boundaries. One more Saturn only slide, and moving now towards the final portion of my talk, which is about how we can remotely sense the solar wind. Wouldn't it be great if you're inside the magnetosphere and you can know what the solar wind is doing? Now at Earth, you can do that because you have a separate spacecraft that's an upstream monitor. We don't have that at the outer planets. And so we need to be particularly creative to think about how we can use magnetospheric measurements to tell us what's going on outside. And there was a really nice paper written by Elias Roussos in 2017, using data from the energetic particle instruments on Cassini, which can make measurements of things called solar energetic particle events and galactic cosmic ray transients. And these type of events are linked to very energetic processes in the heliosphere, like coronal mass ejections and co-rotating interaction regions. So here's a kind of a cartoon showing the sun emitting a large coronal mass ejection, And these are sort of some associated profiles of what we call these SEP or solar energetic particle events. And we can also measure things like Forbush decreases, which are linked to galactic cosmic rays. And so they show up in these traces from the energetic particle instrument on Cassini. And in this paper, they produced a list of all of those events, which again is really useful for anyone who wants to explore further case studies of how, for example, a big CME can change the dynamics in Saturn's magnetosphere. Okay, I just want to talk very briefly about radio and auroral emissions before I finish up. So another great way, another great remote proxy for the solar wind influence at the giant planets is looking at their radio emissions. And so Saturn has a radio emission called Saturn kilometric radiation, or SKR, and it is a cyclotron maser instability generated emission. It is its source is on field lines which have their feet in the auroral zones, and it's a highly beamed emission, and it pulses at or close to the planetary rotation period. That's a whole other seminar which I will not get into today. But it pulses regularly. It has some link to the rotation of the planet. But in terms of solar wind influence, it's been known since the 80s that the energy associated with this Saturn kilometric radiation is highly correlated with things like solar wind ram pressure and IMF magnitude. And when Cassini arrived at Saturn for the first time, this is the Saturn orbit insertion interval, we can see the interplanetary magnetic field strength here. We can see Cassini crossing the bow shock, crossing the magnetopause, closest approach to the planet, and then outbound pass, crossing the magnetopause again. You may remember when I was talking about the phasing of compressions way back at the start of the talk, I mentioned that we predicted that there would be a solar wind compression at some point during Cassini's Saturn orbit insertion maneuver. And indeed, that prediction was borne out by the SKR data. So what we're seeing here is just frequency versus time from the radio instrument on Cassini, and we see a huge intensification and a change in the frequency of the SKR associated with this disturbance in the magnetic field trace from Cassini. And so the SKR at Saturn is a great proxy for what is going on in terms of solar wind driving. At Jupiter, it's slightly more complex. So Jupiter's radio emissions have a lot of different components. Here's a figure showing radio emissions from different planets in our solar system, so flux density versus frequency. And Jupiter has a very broad spread in frequency, and you can get a sense of that here in this frequency time spectrogram. All different types of emission, decametric, hectometric, kilometric, some produced by Io, it's kind of illustrated in this cartoon here, some not linked to Io, so some linked to the solar wind. And there's an awful lot going on in this figure on the bottom right, but this is a study which focused specifically on how Jovian radio emissions can be linked to solar wind conditions. And so what's being shown here in the dashed lines on the top is the interplanetary magnetic field strength recorded by the Cassini magnetometer, propagated to Jupiter. And you can see, compressions and rarefactions. And then we've got the radio power from Galileo and the radio power from Cassini. And broadly speaking, the largest peaks in the radio power, which are the non-Io peaks, are found to correlate well with the arrival of interplanetary shocks. So I would say that the radio emissions at Jupiter are more complex, but we also have an amazing opportunity to study them because we can study them from space. So here's data from Cassini, but we can also study them from the ground. And we can see that sort of in this figure because all of the other planetary radio emissions are lost due to the ionospheric cutoff. So they're not visible from the ground on Earth, but Jupiter's radio emissions are. And just last month, we actually used the LOFAR radio telescope. There is a station in Ireland, in Birr, and we used that to make a measurement of Jupiter's radio emissions while Juno was at Perijove. and we're still analyzing those, but it's great to be able to look at Jupiter both from space and from the ground. Okay, last but absolutely not least is the Aurora. So I couldn't possibly do it justice in 2 slides, but just to give you a flavor, for Saturn, the ultraviolet aurora is associated with the location of the open-closed field line boundary. So in this cartoon here, we see regions of closed magnetic flux in red and open magnetic flux in blue. And then this view down onto the North Pole showing the open-closed field line boundary where the auroral emission is thought to emerge from. And so what that means is that the dark inner ring inside the main auroral oval is corresponding to how much open flux is contained in the magnetosphere. And the latitude of that aurora is constantly changing. And that's reflecting the balance between dayside and nightside reconnection and giving you a sense of what the solar wind is doing and driving the magnetosphere. But at Saturn, the aurora is also highly variable in morphology and brightness. We see things like these really bright dawn storms, which actually made the cover of Nature magazine. And then we see all kinds of morphologies, including sort of spiral shapes evolving. And so the solar wind definitely has an influence on the UV aurora at Saturn. And you have a look at these papers and more if you want to read a bit more detail. At Jupiter, again, complex. Jupiter's aurora is different to Saturn's. Jupiter's main UV emission, some call it an oval, but I think these days main emission is used more commonly, is formed due to co-rotation breakdown, as opposed to being solar wind driven. But there are some very variable polar emissions at Jupiter, which can be linked to solar activity. And again, I would direct you to this review and some of the references contained within, and some of the more recent observations that are made with Juno and associated HST campaigns to give you a sense of how our understanding of the solar wind influence of Jupiter is developing. But we also have X-ray emissions at Jupiter. We can see Jupiter's X-rays with telescopes like Chandra and XMM. And we find that Jupiter's X-rays in the auroral regions are variable and highly pulsed. But we also see X-rays from Jupiter's disk, and they directly reflect solar activity. So they're a really good monitor of solar X-ray flux. There's a pretty direct correlation there. And again, I would direct you to this review if you want to read a little bit more. Okay, so my last thing that I want to say is, I've talked at length about different ways that we can monitor the solar wind, that we can measure it upstream of planets, that we can infer what it's doing by measurements at the magnetospheric boundaries, and that we can remotely sense things like the aurora and use those to understand how the magnetosphere is responding to the sun. But we have a great opportunity coming up in November of this year. So maybe 2020 hasn't been all bad. So this November, Saturn will be situated in Jupiter's magnetotail, and this occurs once every 19 years. This will be the first time when there will be major observation campaigns of the aurora. And so there's a big Hubble campaign being led by John Nichols at the University of Leicester. And some of the science questions that campaign is aiming to answer include, what is the effect on the magnetosphere when the solar wind driving is eliminated? So we're expecting Saturn to lie way down the end of Jupiter's magnetotail. Here's a sketch of what Jupiter's magnetotail is like from the New Horizons measurements, but Saturn is way, way further down there. And it can help us to answer basic questions like, do we even need solar wind interaction to have an aurora in the first place? Is that a requirement or not? And so this campaign will hopefully answer some of those questions and potentially be complemented by infrared and maybe even X-ray observations of Saturn at the same time. So to finish, I'll just say that I've tried to give you a flavor of what we understand of the nature of interplanetary space upstream of Jupiter and Saturn. we've looked at the magnetospheric boundaries. For example, for Saturn, we've looked at lists of bioshock and magnetopause crossings and magnetosheath measurements and what they can tell us about the upstream medium. And then thirdly, I touched a little bit on remote sensing, so using energetic particles as tracers of solar activity and using dynamic radio emissions and auroral emissions to give us a hint of what's going on. But certainly when we place Jupiter and Saturn in the context of other magnetospheres in our solar system, it's clear that the solar wind can have an impact, but it's always that competition going on between external and internal influences. And I think I'll stop there. Thank you.
Thank you so much. That was really interesting and a really clear overview of everything. I'm just going to do my applause reaction. Great, so thank you. So now we'll go into question time. So if you have a question, you can just use the hands up function, and I should be able to see that, or alternatively, you can just pop your question into the chat and I can read it out for you. So go ahead with that. I'll just give everyone a few minutes, well, a minute to bring that.
I think I'm going to turn off. I'm sorry that the subtitles were out of order with what I'm saying. I'm reading them and it's like apple juice. I think I said apogee there, but anyway, hopefully that wasn't too distracting. But
no, it was fine. There was one I think where I called shocks sharks, which was nice.
Well, yeah, that's my poor diction. So yeah, that's my fault. Shall I keep sharing my screen or stop sharing?
Maybe you can keep sharing it in case you want to refer back to any plots.
Yeah.
Do we have any questions? I can't see any coming up. If not, I can ask my question first while we wait. So you mentioned about how Kelvin-Helmholtz instabilities are really important for transferring mass from the solar wind to the magnetosphere. Does that process impart any like dawn-dusk asymmetries into the magnetospheric plasma distribution?
Yes, potentially. So actually, some of the experts in this in the UK are based at Imperial. So I know Adam Masters and Harry Manners have been working a lot on this topic, analysing data from Cassini at Jupiter, because that actually was able to sample the dusk flank. So most spacecraft tend to get good coverage of the dawn flank, but perhaps not so much of the dusk flank. And I know that they have been looking at instability to Kelvin-Helmholtz and how that might be linked to other processes, including things like ULF waves. And at Jupiter, we've been looking at that from the perspective of the X-ray emissions to try to understand how the X-ray emissions are pulsed and how they are linked to those kind of wave processes occurring at the boundary. I think there's, certainly from my perspective, I still have a lot to understand about what makes a boundary unstable to Kelvin-Helmholtz, because you have to consider shear between the planetary plasma that's rotating or sub-co-rotating with the planet and the solar wind plasma. And that, of course, you would expect to be different at dawn and dusk, and so there to be some asymmetry there. But I think part of the reason why there isn't a perfect understanding of that dawn-dusk asymmetry is an incomplete amount of balanced spacecraft coverage on those two flanks. Mm-hmm. So still a bit to know, I would say.
So we just need more spacecraft measurements.
The answer is always more spacecraft, I think, yeah.
We have a couple of questions in the chat. So from Leia, I hope I said your name right. When Saturn is going to be in Jupiter's magnetosphere, is the magnetosheath, I think MS, is the magnetosheath of Saturn going to inflate? Oh, sorry. Is the magnetosphere of Saturn going to inflate due to the lower gas pressure in the absence of solar wind? Leia, feel free to say that if I missed anything out. Magnetosphere,
yeah. So quite possibly, yes. What we kind of have to go on at the moment is measurements that were made by Voyager when this happened 2 cycles ago, two times 19 years ago. So those measurements seem to indicate really, really low densities in Jupiter's magnetic tail, but also possibly pointing at the tail of Jupiter kind of flapping slightly, so that over, you know, a week or even 2 weeks, Saturn might alternately find itself every couple of days in Jupiter's magnetic tail, and then maybe in the solar wind, and sort of in and out. So certainly if you see a very, very low pressure in Jupiter's magnetic tail, then that would potentially imply a significant expansion of Saturn's magnetosphere, which might result in, you know, severe dimming of the auroral emission. Then you have to wonder what happens if Jupiter's magnetic tail flaps away, so that Saturn then finds itself in the solar wind, where you have a very different dynamic pressure. So if that's the case, would you perhaps see a really strong compression of the magnetosphere, even a sort of a shock type scenario, where then maybe you have really bright aurora? It's a great opportunity to answer some of these questions which just haven't been tested before. But yeah, certainly Jupiter's magnetic tail provides a unique environment with parameters which are unlike what you would see in typical solar wind.
Great, that's really interesting. Exciting to see what results they come out with.
Yeah, I think Johnny is the person who will be leading this from the Hubble side, so you can email him.
Yeah, he can give a seminar afterwards.
Yeah,
just volunteered him.
That's fine. Yeah.
We also have a question from Maria. So we touched on this slightly when we were talking about the dawn-dusk asymmetries, but Maria's asking, in an ideal world, what data would we need to answer some of these questions you highlighted? So in particular, solving the external-internal driving conundrum.
Yeah, okay. So that's a great question. For dawn-dusk asymmetries, yeah, you know, it's great if you can have coverage at both flanks. Of course, in an ideal world, you have a permanent upstream monitor at Jupiter and Saturn, you know, a bit like what you have at Earth with ACE, or, you know, what's planned for, had been planned for Mercury, with having an upstream monitor there. Because the difficulty with the solar wind models that I mentioned is that while they can provide you with estimates of solar wind velocity or temperature or density, they don't do well with the IMF components in particular. So you really have no sense from the models of what the IMF direction is, and therefore what the likely dayside coupling is going to be at any point. So you have a sense of what whether you have a compression by the solar wind, but you don't have a great sense of what's going on in terms of dayside reconnection. So absolutely, an upstream monitor would be a game changer in terms of our understanding of the dynamics of the magnetospheres.
Great. Do you think that's do you think we'll see that sort of in our lifetimes, them sending a mission with an upstream monitor?
Probably not. Well, it's tough to say. I think a lot of you know, planetary science budgets, there's obviously a lot of interest in moons and habitability and some of the more geological aspects of planetary science. And so there's always that tension between having, you know, it's expensive to get there, and having a spacecraft and instrumentation that's targeted towards space plasma physics, going hand in hand with a mission that's targeted at you know, planetary composition and moons and geology. And so certainly it's worth trying and making that case for an upstream monitor, but if it will happen in my career time, I don't know. I'll be 40 soon, so I don't know. Maybe not.
But we can hope.
Yeah.
There's no other questions in the chat. If anyone does have a question, add it in now or put your hand up. We'll just give everyone a few minutes. If not, maybe we should wrap up the seminar here now. So I just wanted to say thank you again for giving us such an interesting and excellent seminar. And thank you to everyone who came along and listened and asked questions and got involved. The details for the next seminar will be circulated to the MIST mailing list. And you can always check out our website as well for dates of all the upcoming seminars, as well as links to watch the previous seminars on our YouTube channel. So that's it, everyone. Thanks and enjoy the rest of your day.
Bye, everybody. Take care.
Bye.